Here we go. By the way, if you have any questions, please put them in. Please open your microphone and pose them, because when I'm using my writing paper, I don't see the Zoom screen. But anyway, let's get on with the program. What we will do today is talk about cardinal arithmetic. You have seen a little bit of that in the previous weeks. And today we will talk about the continuum function and cardinal exponentiation. So what you learned from Benedict's lectures is this. That was the easy bit of
KP.
Yeah.
Your notepad is not yet sharing.
Right. That's a very good remark. Here we go. Now it's visible, I hope.
Yes, it is.
Okay, here we go. So what do we know? What is the easy bit that we know for infinite cardinals? And I'm not going to do all kinds of special pluses or multiplication signs. What I just want, I'm just writing this down to emphasize that normal arithmetic, addition and multiplication, is easy. If we have two infinite cardinals, we take the maximum of the two, and that happens to be the product and the sum. In terms of Alephs, we could write this as I'm just repeating myself here. If I know that my cardinals are Alephs and I want to know what the result of the operation is, I just take the maximum of the two ordinal indices, and that will point to the Aleph that I'm going to get. So we have an easy function that tells us, given alpha and beta, what the result of the arithmetic operation is when we apply it to Aleph alpha and Aleph beta. We get Aleph maximum of alpha beta. Now, what we do not know is what gamma do we get when we calculate Aleph alpha to the Aleph beta. We do get a cardinal, we do get an Aleph, because what I should write down here at the top we are assuming the axiom of choice today, and we're working from chapter 5 in Jech's book, Axiom of Choice and Cardinal Arithmetic. We know that it is an Aleph, but we don't know which one.
I can ask something a bit more general. Will these slides also be uploaded on ELO? Okay, thanks.
I will turn this into a PDF, and that will appear on the ELO site. Yep. Okay, and even so, what we know well, of course, we have the special case, the continuum function, so to speak, 2 to the Aleph alpha, We happen to know that it's equal to Aleph alpha to the Aleph alpha. But it's also an Aleph. Which one? So what are we going to do today? We're going to study study the continuum function, the one that sends kappa to 2 to the kappa, and exponentiation. And so what we will see, so that's a function of 2 variables. What we will see is that we actually we cannot really determine which index will appear with our Aleph when we say 2 to the Aleph alpha equals Aleph gamma. What we can say is something about the global behavior of that function. If the function behaves like this in that area, then we can deduce that it behaves like that somewhere else. Most of our results will be conditionals. If this happens, then that happens. If this happens, then that happens. And where does that come from? Well, that comes from what we will do in a few weeks. We'll discuss the forcing method, and the forcing method will help us show that very many of those conditions that we pose are actually possible. So there is lots of variation in the behavior of the continuum function and the exponentiation function. But we can pin a few things down. And that is what we will do today, using relatively elementary methods. Yep, my preparation here. But first, and we're going to need that while we are working, a bit more about cofinality. So remember, just the cofinality of kappa was defined as the minimum cardinality of a cofinal subset of the linearly ordered set, that is the cardinal kappa. We have a few characterizations, and during last week's group interaction, you played around with some of those formulations with varying success, because we were sometimes a bit optimistic in the formulations of the problems, but I hope everything worked out in the end. Equivalent formulations, well, this one was also done by Benedict. There is an increasing cofinal map from gamma to kappa, the smallest gamma that you can use to find a strictly increasing cofinal map into kappa. What we will use, and this is something that will occupy you during the group interaction this week, there's another one. minimum cardinal, because what I'm going to write down only depends on the cardinality. This is a very long definition, but never mind. Such that what the minimum lambda for which we can find a family of subsets of kappa, such that what? Well, the union of those sets is the cardinal kappa, is the set kappa, and every one of those subsets has cardinality less than kappa. This is almost a definition that doesn't use the ordering. We simply want to split kappa into small subsets, each individual subset cardinality less than kappa, and we wonder how many we need. Well, if kappa is regular, we will need kappa many. If kappa is singular, we can do away with fewer. Okay. So this is going to occupy you during the group interactions, but we're going to be using it a few times. And I also want to emphasize something that will be used later also when we're doing the forcing bit. If you calculate the cofinality of kappa, then you get the cofinality of kappa back. Think about it, and you will see that this is clear. And what we didn't quite emphasize, but what we use all the time, is that the cofinality of kappa is actually a regular cardinal, because it is its own cofinality, and kappa is regular. And of course, if we say regular, if the cofinality is equal to kappa itself, then it's singular if the cofinality is smaller than kappa itself. So, and this is usually the way that people talk about regular and singular cardinals. The cofinality is equal to the cardinal itself, or the cofinality is smaller. And occasionally we will use the union of subsets formulation. All right. So what can we say about 2 to the kappa? Let me see. And what can we say about cardinal exponentiation? What we already know and it does no harm to repeat this once more. We already have this. If kappa sits below 2 to the lambda, then kappa to the lambda is 2 to the lambda. What does that mean? Well, it means that in certain cases, we can reduce the cardinal exponentiation to the calculation of 2 to the lambda. It doesn't really say that we know exactly which Aleph kappa to the lambda is. It just tells us you need to find out what 2 to the lambda is, which Aleph that one is. So in this case, if kappa is, relatively speaking, not too big with respect to lambda, we only need to look at 2 to the lambda. So more interesting, what can we say about kappa to the lambda if we know that 2 to the lambda is smaller than kappa? Can we then deduce something? Well, we can deduce a little bit. I'm going to do the obvious thing first. No matter what you do, kappa is less than or equal to kappa to the lambda. Remember, the definition was the set of all functions from lambda to kappa. That cardinality of that is the cardinal power. And so if the family of all constant functions has the same cardinality of kappa, so we get this. What we also get is if 2 to the lambda is less than kappa, then we know by Cantor's theorem that lambda is way smaller than kappa, of course. So kappa to the lambda is less than or equal to kappa to the kappa, which happens to be 2 to the kappa. Here is at least one piece of information. We know that kappa to the lambda cannot go arbitrarily large, arbitrarily far above kappa. It has to stay below or be at most equal to 2 to the kappa. And then, of course, you can ask, is that it? No, there is more. If this was it, then I could stop the lecture right now and we could be doing something else. Here is a theorem that's not from chapter 5, but I want to, we need it anyway. So this is theorem 311 from Jech's book. If kappa is infinite, then what? Then kappa is less than, strictly less than, kappa to the power cofinality kappa. So the cofinality of kappa will turn out to be some kind of breaking point, some transition point in this whole story. The proof is diagonalization, because that's basically the only thing we can do. So we do the diagonal thing. So we have the cofinality of kappa. We take a function from the cofinality to kappa that is strictly increasing and cofinal. Okay, and here is something you have to watch out for. I will try to be as correct as possible, but here is a set of functions. just to stress here, cardinal. You have to live with the overloading of these symbols, unfortunately. So when I say that kappa is smaller than kappa to the cofinality kappa, it means that I'm using the cardinal context. But if I'm saying that I have a set of functions, a subset of kappa to the cofinality kappa that consists of functions, then suddenly that same power is that set of functions. Just be aware of the overloading of the symbols here. And
we have a question in the chat from the Science Park. Types it in the chat, and then we can ask it. And it asks, what is alpha xi?
Alpha xi, well, we have a function, and alpha xi is the value at xi. It's an ordinal below kappa. This is my shorthand for a function. It says xi gets mapped to alpha xi, and the domain is the cofinality of kappa, and the codomain is kappa itself. But it's a function that has no real name. I could have called it f, but I'm going to construct an f, so I'm not using that letter here. We construct we're going to construct a function that is not in the family f. Well, we have a family of functions of cardinality kappa, and we're going to show that it's not the whole thing. How do we do that? Well, how shall I do this? Let's say beta. We have kappa many functions, so we enumerate the family by doing f beta, beta less than kappa. Alrighty. And so how do we make our function from the cofinality of kappa to kappa? So the xi refers to a member of cofinality kappa, which happens to be an ordinal. And so what do we want? We want to avoid we don't want fxi to be among these numbers, because then we can say, well, f is not equal to f beta for any of those betas. So what do? We take the minimum of kappa minus this particular set. This set here has cardinality strictly less than kappa. Why? Because alpha xi is a member of kappa. It's smaller, kappa is a cardinal, and so this set is not the whole thing. And f xi is well defined. And now we see that the alpha xi's were cofinal, so they're going to be xi's that are bigger than beta. And from that moment on, f psi is no longer equal to f beta of psi, and that means that f is not equal to that beta function. And so f is not a member of F. Okay, so what does that tell us? That gives us another piece of information.
So I think you mean F is not in the big F?
Right. We get more information. If the cofinality of kappa is less than lambda, then kappa is less than kappa to the lambda. And so we're still, of course, we are in the situation that 2 to the kappa is less than 2 to the lambda is less than kappa. We're only, for now, we're only interested in that situation. The other one we dealt with. So we have, like I said, we have a little bit more of information about the behavior of the exponentiation. If lambda sits between the cofinality of kappa and kappa itself, it may be the cofinality of kappa, then at least we know that kappa is less than kappa to the lambda. Well, let's underline that so that we know that we have discovered something. Okay, for later, we need still more notation and some notion, both of those. If we have a set whose cardinality is at least lambda, and lambda is our cardinal, then we have the following things. The family of subsets of A that have cardinality exactly lambda, we collect those in this abbreviation here. And now you can, for yourself, invent what these mean. You will find these notations all over the place in set theory. They're useful abbreviations, but we'll be working with the first one mostly today. And in the book, we will find this useful lemma. If we have, we're stuck, usually kappa and lambda here are infinite cardinals. If they can be finite, you will notice because we will have a finite bound for them here or there. But if we have infinite cardinals and we're looking at all the subsets of kappa that have exactly cardinality lambda, then there are this many of them. And how does that work? Well, here we go. Let me, what did I do? All right. if we look at the set of functions interpretation, then kappa to the lambda, the set of functions is a subset of I should turn that around probably. Every function from lambda to kappa is a set of ordered pairs. The first coordinate is an element of lambda, the second coordinate is an element of kappa. But that function has to have a pair for every individual element of lambda and exactly one. So every function has cardinality lambda in this particular case. But kappa is at least lambda, so there is a bijection between lambda cross kappa and kappa because lambda times kappa cardinality-wise is equal to kappa. It's equal to the maximum of the two. So there is a bijection between the two. And there we have it. There we have the first inequality. The cardinal kappa to the lambda is less or equal to the cardinality of that family of subsets. So here, what was the color that I used? I forgot. But, here it is. So that's one inequality. The other inequality really uses the action of choice in a very obvious way. How is that? Well, if we take x in, whoops. For every function, for every set of cardinality exactly lambda in kappa, there is a function from lambda to kappa that has that set as its range. There is even an injective function that does that. But given a set X, there can be very many Fs that do this. So okay, we'll stop doing this later, but for now, let's try and keep this up for a moment. The action of choice gives us an injection from kappa to from the lambda-sized subsets of kappa into kappa to the lambda. There we have it. We have the reverse inequality, and then we apply the Cantor-Bernstein theorem to get the equality. As you will see in the proofs that we will do for the rest of this afternoon, the Cantor-Bernstein theorem is used quite a lot because most of the time it's way easier to give injections from A to B than it is, and an injection from B to A, than it is to give an explicit bijection between the two. But like I said, that will be we will see that happen many times. All righty. Finally, we need one piece of notation still, and then we still need a few more notions, but then we can get to work. Oops, let's keep that black. Kappa to the less than lambda is the supremum of all the kappa mu's, kappa to the mu's, where mu is less than lambda and mu is a cardinal. We're going to need this notation too, because lambda could be a limit, and then how do we calculate some of those powers? And this power will help us in calculating kappa to the lambda at times. And we shall see in a moment if you want to calculate kappa to the less than lambda, you can also look at the subsets of kappa that have cardinality less than lambda. That family has that same cardinality. And we'll be using that idea a few times in what we will be doing. Okay, we're still not ready yet to start our calculations, to start trying to figure out how kappa to the lambda and 2 to the lambda might depend on other values of that function. What else do we need? We need the following. Products and sums of arbitrary families of cardinals. Okay. So we have and the set is indexed, so maybe we should actually turn it into a sequence, but okay, the ordering is not completely necessary there, but we have an indexed set of cardinals, which means that it can be the case that some points in the set will be indexed more than once. Because, as you will see in a moment, that's quite useful to have. What would be the sum of those cardinals? Well, I'm doing it slightly more efficient than Jech does. There is a discussion in Jech's book about the axiom of choice being used here to show that the definition is okay. But since we're taking the cardinal of cardinality of an arbitrary set already, I'll leave that out. We take disjoint copies of the cardinals kappa I. And how do we do that? Well, we simply multiply by the index. That's the easiest way to do that. Now, suddenly those sets are disjoint because the indices are all distinct. There is no double index going around. And we get a set just like we defined addition and everything in primary school. We take disjoint copies of our numbers and union them up, count the union, and that is going to be our sum. And that's the same thing that we do here. We take a disjoint union of our sets cardinals, determine the cardinality of that, and that is by definition the sum of the cardinals. Okay, more for comic effect than anything else. What's the product of the cardinals? Well, it is the cardinality of the product. And so here, the Cartesian product of a family of sets is the set of choice functions okay, in this case, it's the set of functions whose domain is I, and they have the property that f of I belongs to kappa I for every I. That is the Cartesian product of the sets. And so the Cartesian product consists of functions, and therefore I wrote functions below it. Let's prove one theorem about this sum, then we'll have our break. And then we'll continue with the product, a few calculations with that, and then finally we will be able to start calculating our continuum function and our exponentiations. So let's finish with what is in the book 5.8. So we take an infinite cardinal and we take cardinal numbers kappa I, and then we can say that the sum is not so difficult after all. If we take the sum of all these cardinals, then we simply get lambda times the supremum of those cardinals. So sums of cardinals, even if the family is infinite, become relatively easy. And so how does that work? Okay, kappa positive is not really necessary, but that's the only, we need that in one case. Okay, so how does the proof go?
Sorry, can I ask something?
Yeah.
This supremum, that's where Benedict just did the union, right? That's
right.
The same thing.
Yeah.
Okay.
I'm more of the order language in this case. But indeed, it's the smallest cardinal above all the kappa I. Well, it's the smallest ordinal above all the kappa I, but it happens to be a cardinal. Right. So here is, and we call that supremum, we call that mu. Okay, so mu is the supremum of those cardinals. And here is the first inequality. If you take that disjoint union of those kappa i's, well, every I is a member of lambda. And so the picture looks like this. This disjoint union kind of looks like this. We have the lambda as a sort of an x-axis, and above every member of lambda, we have a little vertical line of length kappa I. And of course, that all fits in the rectangle lambda cross mu. And so the cardinality of that disjoint union is less than or equal to lambda times mu. How does the reverse inequality work? So we know that the cardinality of that union is less than or equal to the maximum of lambda and mu. Well, lambda is the sum of lambda many cardinals, namely 1, 1, 1, 1, 1 all the time. So there. So lambda is less than or equal to the sum of the cardinals kappa. And what about mu? Well, for every individual j, kappa j is less than or equal to the sum. Okay, but then the supremum of all the kappa j's is less than or equal to that fixed upper bound. We have an upper bound and we have a least upper bound. Well, the least upper bound is less than or equal to the upper bound. And there we have it. Because now we see that lambda times mu lambda times mu, which happens to be the maximum of the two, is less than or equal to the sum of the kappa I. This even works if lambda is infinite, mu could be finite, but then still lambda times mu is the maximum of lambda and mu. And there we have it. Okay, so let's see. No, I think that is what I want to do in the first hour. So in the second hour, we'll do a similar thing for products. And then we will start to use all that in our calculations towards 2 to the lambda and kappa to the lambda. Okay, I pause the recording and we'll have a break until 3:05, I think. Where is the, there you go. I'm resume recording. So, but we didn't do too much. And I'll just repeat what I said a few moments ago. We can now characterize singular cardinals by expressing them as sums of smaller cardinals. And the only way we can do that if we have just as many cardinals as kappa itself. So kappa is singular if and only if you can write it as a sum of fewer than kappa many cardinals that are all smaller than kappa. What I also said is that you can now do, okay, something silly is going on. Okay, there we are. You can also show now the thing I promised a few moments ago, that this family of sets has cardinality exactly kappa to the less than kappa, the material that you need for that we just developed. And what I also just said is that products of arbitrary families of cardinals are as commutative and as associative as you would like. If you split the set of indices into other sets and take partial products and then take the full product of that, the answer is just the same, because there are easy projections between the defining sets. Okay. And now another inequality, which is pretty obvious if I is a finite set, but for the infinite set, you actually need to show a few things. And here is how the proof goes. And I'll split the proof into two cases. Case one, okay, we don't do the case where I has one element for obvious reasons, but what do we do if I has two elements? Well, then I'm going to do something. Let's see, what else do I have? Yeah. Then I have two cardinals and I have their union. And here I have their Cartesian product. And why is this set smaller than the other set? Because there is an injection. I can take the non-zero ordinals and I put them on the x-axis. I can take the non-zero ordinals of kappa 1 and put them on the y-axis. And then I still have my 0 in kappa 0 and I have my 0 in kappa 1. And because kappa is at least 2, I can do this. If kappa 0 and kappa 1 were exactly 2, then I would have 4 points, a blue one, a purple one, an orange one, and a green one, and it would just fit. If I has at least 3 elements, then I can give a general formula for an injection an injection from this union into this product. And you could try and make a drawing of this for I with 3 elements. You make 3 axes and you will see how you can put those points in there. If alpha is bigger than 0, then fi of alpha, what is it going to be? It's going to be a member of that Cartesian product. So it has to be a function. It has to be a function with domain I, and it has to make a choice in every one of those cardinals. Well, I'll choose alpha at the ith coordinate, and I choose 0 at all the other coordinates. This now, fi alpha is a function, and its value at j is alpha. If j is equal to I, then 0 if j is not equal to I. If I comma alpha is different from k comma beta, then I get 2 distinct functions because of the 0 and the alpha and the 0 and the beta at certain points. What do I do otherwise? Well, you saw that I needed to do something special for the zeros anyway in my picture with 2 cardinals. So what do I do here? I do the other thing. I put 0. I still put alpha on the ith coordinate. That's going to be 0. But it would be very silly if I would put zeros on all the other coordinates as well, because then my function is no longer injective. Because then f of I comma 0 and f of j comma 0 would be the same function. So what I do here is this. And now check that this is injective. You can do that just by considering cases. And you can draw a picture, a nice picture if I has 3 elements. And why, so you can see in the proof why we needed 2 elements. We needed the 0 and the 1 to be able to put all the points in the product. You saw that if we had 2 factors, then we had equality. And there is another reason why we need that all the kappas were equal at least 2. If the kappas were equal to 1, then we don't get the inequality that we want, because the sum of 1s is bigger than the product of 1s. Remember that. Okido. What else can we say about this product? Well, we get something quite close to what we had.
Can I ask something about this final note?
Yeah.
So one exclude that all the kappa I or ki, that they are all 1, but it
Okay.
seems that there sufficiently shouldn't be 1.
Yeah. Okay. For the theorem and its proof, it's easy to have all the kappa i's being at least 2, because otherwise the proof will fail. You can consider, in cases of, say, finitely many, you can say, well, if I have that many 2s, that many 1s, or that many 3s, then I can still have the inequality. But you don't get a single theorem that says you always get the sum less or equal to the product. Even with a few 1s and a few 2s, I can arrange it so that the sum is bigger than the product. if I have 2 2s and 10 1s, then I can still get the product is equal to 4, but the sum is equal to at least 10. So you'd have to make all kinds of, distinguish all kinds of cases, and that would make it just unpleasant, at least in my opinion. And this particular one, the one where all the kappa i's are equal to 2 or more, that's the one that we'll be using in a moment for an important theorem. But yes, you can make variations of it with many 1s, many 2s, many 3s, many alepphs, and whatnot. But I can always defeat the inequality by having very many 1s and just a very few kappas that are not 1. All right. We had, for the sum, we had the number of terms times the supremum of the terms. That would be actually the sum. If you look back at 5.8, let me see where it was. Well, here it is. For sums, we could make the calculation easy, take the sum, take the supremum, multiply by the number of terms, and there you have it. If the number of terms is infinite, of course. Do we get that for products? No, not really. I'll give an example in a moment, but I'll give the theorem first. So if lambda is infinite and the kappa i's are non-decreasing, yeah, then and this is something that we'll be using in the calculation of the powers, because you see that certain suprema are equal to certain products. Powers of suprema are equal to products, and that is a very useful thing to have. For example, here is a special case of this equality. If I take the product of all the LFNs and in omega, then I get simply the omega power of aleph omega. I don't get aleph omega, which you would think possibly is the supremum of the partial products. No, you don't have that type of continuity. You get the aleph 0 power of aleph omega. And how does that work? Well, the proof is not that difficult. We have Hessenberg's theorem that says that if I have an infinite cardinal, then it is equal to its own square. And you can get a lot of mileage out of that. If there is a bijection between lambda and lambda cross lambda, then we take the vertical lines and we take them back through the bijection and we split lambda into lambda many sets, each of cardinality lambda. And we note what? Well, If I take the supremum of kappa i's where kappa runs through A alpha, then I get the supremum of all the kappa i's. Why is that? Well, A alpha has cardinality lambda. Lambda is a cardinal, so A alpha must be cofinal. Any ordinal less than lambda does not have cardinality lambda. That means that a set of cardinality lambda cannot be bounded. And now we know that because of the commutativity and the associativity, we can write the product of the kappa i's as a product of products of kappa i's. Okay. And so what do we get? The product of every, okay, let's non-decreasing, and the kappa i's are non-zero. Because otherwise the product becomes zero and we don't have anything. Again, the product of the kappa i's is bigger than or equal to each individual kappa I. So product the product is at least as big as the supremum of the kappa i's. So that's what we do. And here we have our first inequality. The full product is at least as big as the supremum to the lambda. But clearly, each individual kappa I is less than or equal to the supremum of the kappa j's. So if I take the product of all the kappa i's, I get something that's less than or equal to the product of lambda copies of that supremum, and there we have it. So we have roughly the same thing as in the sum, but we need to assume that the sequence is non-decreasing. And if the sequence is not non-decreasing, let's look at this sequence. The supremum is equal to L of 0 of this sequence. It's the maximum. And the product of the kappa n's is L of 0. But and of course, we take lambda equal L of 0 as well. The product of the power of the supremum is 2 to the L of 0, which is way bigger than this product. So we really do need to know that the sequence is non-decreasing. And here comes sort of the final nail in the coffin of many things that of the things that we'll be doing. After this, we will start to reap the fruits of what we have been sowing today. Here is an important theorem. by Hungarian mathematician Koenig from around 1900. He thought he had proven that the continuum hypothesis was false during the International Congress of Mathematicians around, I think, 1900. And Cantor was really unhappy about that. But fortunately, Zermelo found an error in the proof, and the error in the proof became Koenig's theorem. And here is the result. If you have a family of cardinal numbers, so I have an index set I have cardinal numbers kappa I and lambda I for every individual I. And I know that each individual kappa I is strictly less than each individual lambda I. Then the sum of the kappa i's is strictly less than the product of the lambda i's. Notice that we had less than or equal in, where were we in this result? We never said strictly less than, because we can always, with ones and twos, we can make things equal. But here we get strictly less than. So how does that work? Well, the proof says first, without loss of generality, the kappa i's are all bigger than 1. They're non-zero. Why is that? Well, look at all the i's for which kappa I is bigger than or equal to 1. Then what do we get? Well, if I take the full sum, then I have a few zeros. So it's equal to the sum of all the kappa i's where I runs through J. Then if we assume the result for all the kappa i's bigger than or equal to 1, then we get this. And now, whatever you may know, every lambda I is at least 1. If kappa I is equal to 0, then lambda I is bigger than 0, so it's at least 1. So the partial product over J is less than or equal to the full product over I. So we can assume, and it's useful to have, that every kappa I is at least 1. Why is that useful? Because now every kappa I is bigger or equal than 1, every lambda I is at least 2. And here we go. So this is clear. Every kappa I is less than every lambda I. So the sum of the kappas can be at most the sum of the lambdas. On the other hand, we have just shown that if all the lambdas are at least 2, then we get this inequality. And That's what I meant by we're going to need the case lambda I at least 2, just in this particular case here. Okay, we have less than or equal. Now, strict inequality, how do we get that? Well, let F from this disjoint union and we are talking functions here because we want to, we're looking at the representing sets for the sum and for the product. We have a function from the representing set for the sum to the representing set for the product. And we need to show we must show that F is not surjective, not onto. So we need to find a function that is not equal to any one of the F's that is in our family. Well, take an I from I. What can we say? Well, we have again, let's be clear. This is a function. And so we have a value at I. Now, this is a subset of lambda. This is a subset of lambda I. All those values are a subset of lambda I. How many values do we have? At most kappa I. So this is a proper subset of lambda I. We have kappa I many elements of lambda I, and our assumption is kappa I is strictly less than lambda I. So we can take the minimum of lambda I minus this particular set of values. Then G is not equal to Fi alpha for all I alpha. G is never equal to any one of those functions that we had. Okay, now this is for now the best we can do if we're talking about products of cardinals and sums of cardinals. Koenig's theorem is roughly the best we can do by elementary means. There are things we can do with very non-elementary means, but with the means that we have at our disposal right now, this is the best we can do. But it has a few interesting and important consequences. And I want to mention those. And one of them will give us a definite barrier for the behavior of the continuum function. One, well, we get Cantor's theorem back. I, the cardinality of I is strictly less than the cardinality of its power set, 2 to the I. 2 to the I, if all the cardinals in your family are the same, you simply get the power back. And if all the cardinals in your family are equal to 1, The sum is just the cardinality of your set. But here is a more important consequence. The cofinality of 2 to the kappa is bigger than kappa infinite. If you take an infinite cardinal, you take its 2 to the power, you get something whose cofinality is bigger than kappa itself. And where does that come from? Well, and for I in kappa, we take kappa I something less than 2 to the kappa, I don't care. And for lambda I, we take 2 to the kappa all the time. What do we need to show? Well, we wanted to show that the cofinality of 2 to the kappa was bigger than kappa. Well, here we go. We use that characterization of the cofinality that we mentioned a few moments ago. We have fewer, the cofinality is the smallest cardinal we can use to make fewer cardinals, fewer than kappa many cardinals, each smaller than kappa, whose sum is equal to kappa. And there we have it. Kappa does not meet that requirement for 2 to the kappa, so it's less than the cofinality of 2 to the kappa. This is really, really important. What does this say about Cantor's continuum problem? No matter what you try, two to the Aleph 0 can never be Aleph omega, because Aleph omega has countable cofinality and 2 to the Aleph 0 does not have countable cofinality. So it's either smaller or bigger, but it's not equal to Aleph omega, or Aleph omega plus omega, or Aleph omega plus omega plus omega, or Aleph alpha for any countable limit ordinal alpha. Lots of values of 2 to the Aleph 0 are forbidden now. Another one that we saw a few moments ago is that kappa to the cofinality kappa is bigger than kappa itself. Well, you write kappa is equal and what do we, and lambda I you take kappa I to be some family that unions up to, that sums up to kappa, all of them less than kappa, and lambda I, you take kappa itself, and now you apply Koenig's theorem, and you get this inequality back. So the important inequalities that we have, and the one that we got, number 2, are all special cases of Koenig's theorem. And like I said, this is roughly what we can say when we are using elementary means to talk about the continuum function. And where did I write that? Okay, well, let's, I'll come back to that in a moment. actually, this is a good moment to pause. We'll take another 15 minutes, and after that, we will collect all the things that we can deduce from the theorems we have so far. We can see how the continuum function can be computed step by step, and we can see how cardinal exponentiation can be done step by step. And that will be the end of the story then for today. Okay, so I should remember. I'll pause the record, zoom the recording. Here we go. Okay, I already put on my paper, so to speak, the generalized continuum hypothesis, which is one particular type of behavior that we could want from the continuum function. Fortunately, consistent with ZFC. Thank you, Gödel. And it makes life relatively easy. And if you look in Jech's book, Theorem 515 tells us how easy that life is. If kappa and lambda are infinite, then, okay, the continuum function we already have. So how does exponentiation work? Well, we had those cases that we had to consider anyway. So we had the case that kappa was less than or equal to 2 to the lambda, then kappa to the lambda was equal to 2 to the lambda. And in our case, that is just lambda plus, the next cardinal above lambda. So that's easy. We already knew this. Then the second case that we encountered was that there was a breaking point at the cofinality of kappa. If lambda was less or bigger than the cofinality of kappa, something might change. Well, kappa to the lambda is equal to kappa plus. Why? Well, because we knew we already know that, let me erase this and put a nice, we already found out that kappa was less than kappa to the lambda, but kappa to the lambda was less than or equal to 2 to the kappa. Well, there is not much room then anymore if we assume the generalized continuum hypothesis, it has to be kappa plus. And then, of course, we have the case where lambda is strictly less than the cofinality of kappa. And then kappa to the lambda is just kappa. And why is that? Okay, now we have to do a little bit of work. S sets we get that kappa to the lambda is the union of the sets alpha to the lambda, where alpha is less than kappa. Every function from lambda to kappa is bounded. So it is a function to a smaller alpha already. And that means that that means that the cardinals, kappa to the lambda, is the sum of the cardinals alpha to the lambda cardinality alpha to the lambda for alpha less than kappa. How many terms do we have? Kappa. And so we get something like we know that this sum is equal to kappa times the supremum of all those things, but if we look at alpha to the lambda, then that is a set of functions from lambda to alpha. It's a subset of alpha cross lambda, and that means the cardinality is at most 2 to the alpha times lambda. Cardinality alpha times lambda. GCH says that is the plus of alpha times lambda, but alpha and lambda are both smaller than kappa, and that means their plus, the product is the maximum and their plus is less than or equal to kappa. And so this product is equal to kappa because all the individual cardinals are less than or equal to kappa. That means the supremum is at most kappa. So the product is the maximum of the two, which happens to be kappa. So life is easy with GCH. Without GCH, what can we say? Well, we already know for the continuum function that we don't get the cofinality of 2 to the kappa has to be bigger than kappa, and roughly that is it. We can say a few things, but for example, suppose you have a cardinal function that has this property, then there is a model of ZFC and for all regular kappa, you can get, you can get this as your continuum function. For singular kappa, life is more complicated. You can find some of these things in Jer's book, and other things were left out. What can we say more? Well, I just mentioned this, but it is actually a fact. If kappa is less than lambda, then kappa does not have more subsets than lambda. So that is easy to see. We already know. I keep repeating this because it's quite important. And what I've just mentioned is that for regular cardinals, this is the best you can do. Nothing else can really be proven about them. Anything that satisfies these two conditions can be the continuum function for regular cardinals. I will not be able to do that particular consistency result, but it is one that you can study later if you want to. Here is a strange equality. If kappa is a limit cardinal, then 2 to the kappa depends on the smaller powers of 2. You take the supremum of all the 2 to the lambdas where lambda is less than kappa, and take that to the cofinality kappa, and that is what 2 to the kappa is. So here is the beginning of a sort of a recursive way of calculating 2 to the kappa. If kappa is regular, you don't know. Certainly if kappa is a successor, anything goes, as long as you keep to properties 1 and 2. But if kappa is a limit cardinal, then you have suddenly a little bit less freedom. And where does that less freedom come from? Well, again, we write kappa in the usual way. So we take it as a sum of cardinals, and we look at 2 to the kappa. Well, that is 2 to the sum. And cardinal arithmetic works the way it's supposed to work. The power of a sum is the product of the individual powers. I'm not going to prove that. You can do that on a piece of paper about 5 centimeters worth, because all you need to do is make a bijection between certain products. Maybe 5 lines is not enough, is too much. Each individual 2 to the kappa I is less than or equal to 2 to the less than kappa, because 2 to the less than kappa is the supremum of all the 2 to the kappa. Kappas were 2 to the mu's, where mu is less than kappa. Well, and that is our goal. That is our goal power, 2 to the less than kappa to the cofinality kappa. So we have the inequality that we're looking for, but notice 2 to the less than kappa is less than or equal to 2 to the kappa. And of course, the cofinality of kappa is less than or equal to kappa. And again, we use the Cantor-Bernstein theorem to finish everything. So we have 2 to the kappas. Our right-hand side sits between 2 to the kappa and 2 to the kappa, so it has to be equal to 2 to the kappa. And now we are going to get things of the form if then else. First consequence. Suppose you have a singular cardinal and you know that the continuum function is constant on an interval that ends in kappa. Jech expresses this as eventually constant below kappa. So 2 to the mu is constant on an interval of the form lambda cross kappa. So yeah, the graph of the continuum function looks like this. 2 to the mu, oops. If you have cardinals mu, nu, whatever, below kappa but above lambda, then all the values are the same. And the result is that 2 to the kappa is equal to that constant value. And here is one thing that I mentioned during the break. Yes, this is possible. We can, for example, have the case where 2 to the L of 0 is equal to 2 to the L of 1 is equal to 2 to the L of 2 is equal to 2 to the L of 3, and so on and so on and so on, for all the natural numbers below omega. And what this means then, what the theorem says, is that 2 to the L of omega has to be equal to that value as well. And how does that follow? Well, the cofinality of kappa is, well, smaller or larger than this lambda. It doesn't really matter. It simply means that above this lambda, above this cofinality of kappa, we have this constant value. So let's say we have mu bigger than or equal to cofinality kappa, and okay, lambda is a little bit unfortunate. Let's say there is enough Greek letters, a tau, a cardinal tau, such that if mu sits between mu and kappa, then 2 to the nu is equal to that constant value tau. And so what do we know? Well, 2 to the less than kappa is 2 to the mu is equal to tau. Because what was it? It was the supremum of all those values. And once it's constant, we get that. And 2 to the kappa is now 2 to the mu to the power cofinality kappa. Well, mu is less or equal than, let's see. The cofinality of kappa is less than or equal to mu. And so we get 2 to the mu, and there you have it. So that is an explicit formula for 2 to the kappa in terms of smaller 2 powers. And this is what I meant by we're going to have a sort of a recursive computation device going on here. We need another function. We already have Aleph, we already have Beth, And we also need Gimel. And I hope I can sort of draw it correctly. Kappa to the cofinality kappa, this one is going to be quite important when we try to compute the continuum function and when we try to compute exponentiation. Okay. Suppose, so what did we have? We had a singular cardinal and 2 to the mu was constant on an interval. So now we're going to look at what happens if it's not. Kappa a limit and 2 to the nu not eventually constant. Below kappa. So for every cardinal below kappa, there is a slightly larger one where the 2 power is a bit bigger. So this is the only thing that can happen. It can only get bigger. Then, yeah, 2 to the less than kappa is, of course, the supremum of all those 2 to the nus. And important, the cofinality of 2 to the less than kappa is equal to the cofinality of kappa itself, because you have a cofinal sequence below kappa where the continuum function is increasing, and that cofinal sequence has the same cofinality as kappa. Okay, and what do we know about 2 to the kappa then? Well, 2 to the kappa is 2 to the less than kappa to the cofinality of kappa, and that apparently is equal to this, okay, it looks pretty ugly, but it's equal to this Gimel of 2 to the less than kappa. We proved this only for singular kappa, but it's definitely also true for regular kappa, because for regular kappa, cofinality kappa is equal to kappa, so kappa regular. For kappa regular, this is easy. This needed some work for singular kappa. So no matter what we do, if we want to compute 2 to the kappa, we need to know the value of this Gimel function in 2 to the less than kappa. And here is the summary of this all. And now I want to try and save myself a little bit of work. And it should be this one, I think. Right. Here is how you oh, wait a minute, this is not the one that I wanted. No, it is the one that I wanted. Here is a summary of what we can say about 2 to the kappa. And the one thing that you have to realize, if kappa is regular, then kappa to the cofinality kappa is just kappa to the kappa is 2 to the kappa, and that'll tell you that this is true, because the Gimel function is just 2 to the kappa, if kappa is a successor. Successors are regular, so there. If kappa is a limit and the continuum function below kappa is eventually constant, then we have two cases. It could be singular or it could be regular. And what I just mentioned is that we can use that to our advantage. Kappa is a limit cardinal, then 2 to the kappa is equal to the Gimel function if it's regular, and the Gimel function 2 to the kappa is bigger than or equal to 2 to the less than lambda. So that works. And let's see. Okay, let me, I'm not going to talk over this. I'm going to write this down. Certainly 2 to the kappa is at least 2 to the less than kappa. And we prove part 2 by looking at all the inequalities. 2 to the kappa is bigger than each of the individual, is at least each of the individual factors. And if kappa is singular, then let's see, where were we? Then we get the Gimel function at 2 to the kappa. Let me see, where is my, oops, it is constant, sorry. I'm looking at the wrong case. If kappa is singular, then we know that 2 to the kappa is equal to 2 to the less than kappa. If kappa is regular, then 2 to the kappa is kappa to the kappa, is kappa to the cofinality gap. So either way, 2 to the kappa is one of the two factors, and there we have it. And case 3, that is the one that we just talked about. If we have a limit cardinal, then we can calculate the continuum function by looking at the Gimel function of 2 to the less than kappa. So this Gimel function, even though it is somewhat trivial for regular cardinals, appears everywhere in the computation of 2 to the kappa. All right. So on to exponentiation. What can we say when we want to calculate the exponential of our cardinals? Well, we need to note one or two things, and then we can write another summary, just like the one I put up in a moment. One thing that we used a few moments ago, where was this? No, I think I lost it. As sets, kappa to the lambda is when the cofinality of lambda kappa was less than, sorry, if lambda was less than the cofinality of kappa, then we got this equality of those sets here. And of course, we get the same thing when we are looking at, if in particular, if kappa is regular, then this happens for all the lambdas less than kappa. And that is the thing that I wanted to emphasize. So here we go. If kappa is regular, then we get this, and because if lambda is less than kappa, because lambda is then less than the cofinality of kappa, and so kappa to the lambda is the sum. We have seen that already, but I'll just write that down for emphasis, because what happens if kappa is a successor? Suppose kappa is a successor, Aleph alpha plus 1. Then what do we get? Well, all these, how shall I say this? Then kappa to the, and say lambda is Aleph beta, because that is what we're going to be looking for. Kappa to the lambda, yeah. Kappa to the lambda is Aleph alpha plus 1 to the Aleph beta. Okay, now this is going to be really hairy, but never mind. Okay, we use the ordinal sense of omega alpha plus 1. That makes it slightly smaller. And we put Aleph beta here, of course. Now, what do we know? This is a non-decreasing sequence of cardinals. So we know that this is the number of terms times the supremum This is the supremum of all those powers, but we know what the supremum is. The supremum is a maximum, because what is this supremum? This supremum is simply Aleph alpha to the Aleph beta. The supremum is a maximum. The maximum cardinality below Aleph alpha plus 1 is Aleph alpha. So we, in the end, we get Aleph alpha to the Aleph beta all the time. So I'm going to put this in a box. Okay, I'm not going to make it all red because it is about cardinals. This is Hausdorff's formula, which helps you calculate powers of successor cardinals. All you need to know is what happens at the predecessor and multiply by the cardinal itself. So you can now easily calculate what Aleph n to the power Aleph 0 is if the continuum hypothesis holds, for example. Think about it. Okay, let's see if we can get there in time. How much do we have to Okay, kappa a limit cardinal. I wish I could preface these by this is the that formula, this is the that formula, but it's just a lot of tiny details and suddenly they come together in our summaries, and I'll have a summary in a moment. Oh. If we have a limit cardinal and we are sitting above its cofinality, remember we looked a lot at, we're looking at cardinals less than kappa in the general case. We know if kappa is less or equal than 2 to the lambda, then kappa to the lambda is 2 to the lambda, and we're done with it. So this is, in many cases, our standing assumption that we are looking at lambdas below kappa, but occasionally you can write this down in general. Let's see. There we go. Why is that? Well, again, this could be simply a regular cardinal, and then we write kappa as a sum of smaller cardinals that are all of kappa many. But usually this is useful if kappa is singular. And now we can do this Cantor-Bernstein thing again. Okay, now we are doing a power of a product, but since we are looking at really non-zero cardinals, we can now use our formula of a few moments ago. The sum of the cardinals is less or equal than the product of the cardinals. We can certainly assume that all the kappa i's are at least 2 because we want to find our infinite cardinal kappa. And now, of course, we can use the commutativity and all the other properties of cardinal multiplication. And again, each kappa I is less than or equal to the supremum of the cardinals below alpha. So kappa I to the lambda is less or equal to that supremum, which we of course use, and then we get that supremum to the power cofinality kappa. And there is the one that we were looking for. And every alpha is less or equal than kappa. So this whole supremum is less or equal to kappa to the lambda, and lambda is at least kappa, so we have our kappa to the lambda back. Yay, we have, again, we have this cofinality kappa here in the exponent, and there's where the Gimel is going to come back. And so now I'm picking up the theorem. If we have an infinite cardinal, then we can calculate the value of kappa to the lambda recursively as follows. This we know. We have known it for a long time. This has the same proof. If mu to the lambda is bigger than or equal to kappa, then kappa to the lambda is mu to the lambda. And that means if we want to calculate kappa to the lambda, we have to calculate mu to the lambda. Fine. Okay, we go one step down. And then, of course, we have the case where all the values mu to the lambda are less than kappa for all the mu's less than kappa. That is then apparently the remaining interesting case. And what do we get? Well, if the cofinality of kappa is bigger than lambda, then in this particular case, right, when all the mu to the lambdas are less than kappa, if the cofinality of kappa is bigger than lambda, then kappa to the lambda is just kappa. And if the cofinality of kappa is less than or equal to lambda, then we get this Gimel function. But this is in the case where all those lambda powers stay below lambda. And why is that? Well, let me see. If kappa happens to be a successor, then we have Hausdorff's formula. And then we get kappa. So if we have a successor cardinal, then we get our result, because then a successor is regular anyway. If we don't have a successor, then we use, okay, we have to go red again. The set of functions from lambda to kappa is the union of the sets and so on. And then this sum is equal to kappa because all the powers are less than kappa. That's our assumption. How many terms do we have? Kappa many. We get kappa times the supremum, and that is equal to kappa. And if the cofinality of kappa is less or equal than lambda, then we get where is it? We have the older, we have one of our older results, and I forgot where it was. Yeah, it's here. If kappa is a limit cardinal and lambda is at least the cofinality of kappa, then kappa to the lambda is equal, sorry, where were we? Yeah. Is equal to the supremum to the power cofinality kappa. But now the supremum of the alpha to the lambda, alpha less than kappa, is kappa because of the fact that all those powers are less than kappa. And to finish, I'll put another picture in here, and that is the corollary to all of this. And I'll have not much to say about that, but this tells us that this Gimel function is really important. What can our power be? Well, it can be 2 to the lambda, when 2 to the lambda is way bigger than kappa itself. It can be kappa. And then it can be the Gimel of kappa in the particular case we have here, but that's in the case when all the mu to the lambdas are less than or equal to kappa. So it is a Gimel of kappa itself. Or you have this case where there is a mu less than kappa such that this happens, and then you take the smallest mu with that property, let me see, it was if you take the smallest mu with the property that mu to the lambda is bigger than or equal to kappa, then that Gimel is going to be the value of kappa to the lambda and mu to the lambda as well. And that is how the computation progresses through the cardinals. And what we will be doing in the remainder of the course, next week and the week after that, we'll do some combinatorics in preparation of forcing. And in the forcing chapter, I will show, among others, how you can actually get some of those situations that we talked about here consistent, so that what we have been doing here was not empty. All those assumptions that we have been making here and there can be fulfilled. And so all those wild behaviors of the exponentiation and the continuum function are possible. I conclude with just one thing which is useful for the group interaction. There is an assumption which looks like the continuum hypothesis with an S, but the C in this is not continuum but cardinal. It's the singular cardinals or cardinal hypothesis. It's one that should be mentioned, and I mention it to finish. What does it say? The singular cardinal hypothesis says this: something for singular kappas. If it so happens that 2 to the cofinality of kappa is less than kappa, then the Gimel function should have its smallest possible value, namely kappa plus. And you might wonder why somebody would formulate this thing. Well, as you will see in the group interaction, this one makes life easier than the general case. Not as easy as the generalized continuum hypothesis, but relatively easy. It makes for quite a nice way of calculating those powers. And why has this been isolated? It is very hard to make consistently false. It is not provable from ZFC, but proving that it is not provable from ZFC is very, very hard. It needs large cardinals, some of the stuff that we did last year, but not going to do this year. Its negation would be a very strong thing. So in most of the normal models of set theory, this actually happens, and cardinal exponentiation is actually somewhat easier than you would think in general. Unfortunately, we do not have time to dive into this, but at least you will have the opportunity to think about it during the group interactions and get a feel for what this is going to do. Okay, that's it. Let me